board. So as far as the goals for this week, last class, we looked into what's the distribution of a proportion, how does the central limit theorem help us describe it? And then we tried to use that to make some confidence intervals, and we did a hypothesis test. And we only got to one hypothesis test last time for a proportion, so this time I'm going to do another hypothesis test, and then I'm going to talk about distribution for a mean according to the central limit theorem, and then how we use that information to do a confidence interval and a hypothesis test. And we should be able to do a couple of each of those today. Before I actually do any hypothesis tests or confidence intervals, I just want to do a summary of what chapter 6 says. So here and here. So inferential statistics summary. I'd recommend writing this down. It's kind of a good cheat sheet on how to do most of what we've been doing for the last few weeks. So the newest thing we've been looking at the last 2 weeks is the central limit theorem. Clean up my screen here. I am recording, right? Yeah. Central limit theorem. And what it says, for a sufficiently large sample size, the distribution of the sample statistic for the population, and usually I would say population parameter. Our population parameters tend to be either means or proportions. So population, mean, or proportion is normal. And then it goes on to say a couple of other things. So it goes on to talk about what the middle of the distribution should be roughly, and what the spread of the distribution should be. So for our middle, so normal with middle, and the middle is either going to be P for a proportion, which we approximate with P hat from a sample. Remember, we have population versus sample. Or the middle is going to be the mean. And the mean should be roughly the population mean, which we approximate with the sample mean. And again, this middle here, P stands for proportion, And so that's the middle of the distribution. Normal means bell-shaped. It talks about the standard error. So the standard error for a proportion we went over last class, that's going to be that big old square root with P times 1 minus P in parentheses over N. And sometimes if it's a hypothesis test, we think we know what P is, and if it's a confidence interval, this is our best estimate. So in here is either P or P hat, depends on the scenario. Or if it's a mean, and this is what we're going to work on the rest of today after I do one more example here, it's going to be the standard deviation of the sample, that's what S is, over the square root of N. And again, N, remember, anytime we see an N, that's sample size. So I'm just going to write this in slightly different words. S stands for sample standard deviation. And N is the sample size. So on the bottom, we have the square root of the sample size. So that's kind of the essence of the central limit theorem. And then just a couple of other notes to help us with this. So let's draw the dotted line there. I didn't go over this last time, but I'm going to mention today. The book talks about it right in the beginning of chapter 6. We can only do this with a proportion if we have certain constraints on the sample size and the proportion. And those constraints are that if you take n times p, so p would be the proportion of favorable outcomes, like maybe it's the number of cats, the percent of cats that hunt from your house. If you multiply n by that, instead of getting the proportion of cats, you get the number of cats, right? And that number has to be greater than or equal to 10. And if there's a proportion of cats that do hunt, there's going to be a proportion that do not. That's what we get with the 1 minus. So if we take n times 1 minus p, that would be the number of cats who don't hunt. That also has to be greater than or equal to 10. So if either of the numbers we're talking about, the number in favor or the number against, are less than 10, then we probably shouldn't be using this technique. We need to use another method for trying to either run a hypothesis test or to do a confidence interval. And often a simulated one, a bootstrap one can work for that, which is what we started off doing. But these formulas don't work as well if the numbers are too small. As far as the constraints on when we can get away with this, one of them really, right, sample size is definitely an issue. And usually we say we want the sample size to be at least 30. Okay? And if the sample size is less than 30, then that's where kind of down here we run into problems. Regardless of whether the sample size is 30, when we're doing means, instead of using what are called z-scores, we're going to switch to t-scores from a t-distribution. And I'll show you how we do that today. A t-dist is a special kind of normal distribution. And I'll explain why we need that in just a little bit once we get to that next example. Some other notes to add to this. For confidence intervals, our formula is always whatever the sample statistic is, oops, missed a couple letters there, plus or minus our z-score times whatever the standard error is. Okay. And we have formulas for the standard error that we can apply from the central limit theorem, and then we just have to decide how to get the z-score. And so those z-scores are either from a normal distribution, like for a proportion, or they're from a t-distribution. So here I'm going to say the z comes from a t. And let's see. In a spreadsheet, it would be t-dist that we'll play with, or t-inverse, depending on what we're doing.
On the sample statistic, it says plus or minus z-score. Is that time?
Yeah, I can't, I'm too far. I can't hear you. Speak again.
On the sample statistic,
Yep.
It says plus or minus z-score. Is that times SE?
Yeah, that's a times
Okay.
the SE. And I want to remedy this here on a spreadsheet to get a t-score. We use the t-inverse. And we'll get to that in just a little bit. And then hypothesis tests. We calculate what's called the standardized test statistic. We started doing that last week. Sometimes it's just called the test statistic versus sample statistic. And that's either a Z or a T score, depending on whether we're doing a confidence interval whether we're doing a proportion we would call it a Z, and for a mean, we call it a T. And to calculate those, that's always the sample statistic minus the null value divided by the standard error. And again, if we're talking about a mean, we call it a t-score. If we're talking about a proportion, we call it a z-score. And that is a summary of stuff we've done before and the new stuff for this week from the central limit theorem. All right, so let's do an example of a hypothesis test for proportion, and then we'll move on and do some confidence intervals and hypothesis tests for mean with this new information here.